In this video, I'm going to go over the derivatives of trig functions. And that's going to include two different topics. First, what are the derivatives of those trig functions? And yes, we're talking about all 6 basic trig functions. And then I'll do a slew of examples. Let's get into it. Before you even start taking derivatives of functions that have trig functions within them, you need to know what the derivatives of the trig functions are. So on the left side, we will start out with sine, cosine, and tangent. So the derivative with respect to x of sine of x is cosine of x. And the derivative with respect to x of cosine of x is the opposite of sine of x, otherwise known as the negative sine of x. The last one down here on the left is the derivative with respect to x of tangent of x. And when you take that derivative, you'll get secant squared x. Then with the reciprocals of these 3 functions that we started with, the derivatives will look a little bit different. So the derivative of a cosecant function will yield the function negative cosecant of x cotangent of x. When you take the derivative of a secant function, you'll get secant of x times tangent of x. And lastly, when you take the derivative of the cotangent function, you will get negative cosecant squared of x. And I'm not going to end there. There are a lot of little patterns that I see, and maybe you can find some on your own as well. But one of the patterns that sort of immediately jumps out to me is sine and cosine kind of cycle back and forth. Derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine would just be this derivative with a negative in front of it would be negative cosine, which is kind of weird then when you have a negative cosine and you take the derivative of it, it becomes a positive sine. So they just kind of cycle one after another. Another thing I see is if you take the derivative of any type of tangent function, so here we have tangent and here we have cotangent, you will get some kind of secant function. So derivative of tangent turns into secant, and derivative of cotangent turns into cosecant. But what's really interesting about this too is that the secant and the cosecant will be squared. And kind of similarly along the lines, if you take the derivative of any type of secant function, secant or cosecant, you'll end up having 2 trig functions multiplied together. One last thing that might not be as obvious is when you're taking the derivative of a co-function, that's the cosecant, cosine, or cotangent, you'll notice that all of these have negative derivatives. I'm wondering if y'all can find any other patterns among these. Now that you've seen all of the derivatives for the trigonometric functions, we can start taking derivatives of functions that have trigonometric parts scattered about them. For example, we're being asked to find the g prime of t, otherwise known as the first derivative of g of t, which is this function 1 over cotangent t minus 3 over t squared. And you'll notice that this part doesn't necessarily have a trigonometric part to it. And the way that we've dealt with these in the past is you notice the variables in the bottom, and you can rewrite that as being in the top of the fraction if you just make the exponent negative. So now it is in a form that the power rule can be used on that term. And we can do something similar with the first term here. You do not have to use the quotient rule for 1 over cotangent of t. What you can do instead is use the reciprocal function of cotangent t to get tangent t. And so now the quotient rule is avoided altogether. And now that we have it set up in a way that we can continue with actually finding the derivative, we'll do that. So g prime of t, if we take the derivative on the left, we will get g prime of t. And if we take the derivative on the right side of this equation, we will get the derivative of tangent of t is secant squared of t. And then the derivative of -3 times t to the -2nd power will be plus 6t to the -3rd power by the power rule. And then we just have to take care of this negative exponent here by bumping the t to the -3rd power back into the denominator and getting finally secant squared of t plus 6 over t cubed. And there's our derivative. And on this slide, I've got a couple more examples here. It just says find the derivative of each. And so the first function we have is y equals cosine times tangent x. And while, yes, you could use the product rule here and simplify, what you could also do is recognize that this function is cosine of x times, if we break tangent down into sines and cosines, it would be sine of x over cosine of x. And in this case, you can see the cosines reduce. So really, this function that we started with over here is equivalent to sine of x. So I know for a fact that the derivative of sine of x is cosine of x. And this probably messes with you. It's messing with me right now. I see y equals cosine of x times tangent of x. And when you take the derivative of it, you get cosine of x, like that tangent was never even there. That's messing with me. That's just a coincidence that that happened. The math to see how the cancellation works and then taking the derivative of the sine is over here. All right, the next example, we have a different function. M is in terms of p. So here we go. We have m equals -145 times the quantity 1 minus cosine of p, close it, times the quantity 1 plus cosine of p, close it. And again, you can use the product rule if you want, and then you can simplify it. But again, with this one, you might notice that if you distribute the 1 to both terms in the second binomial and the minus cosine to both terms in the second binomial, you might recognize this factored pair as a conjugate pair, aka in this case, the difference of squares factors. And it multiplies out very nicely just to be -145 times 1 minus cosine squared of p. And then through remembering your Pythagorean trigonometric identities, that sine squared p plus cosine squared p equals 1, you can subtract cosine squared p from both sides to get 1 minus cosine squared p, and all of this in here just equals sine squared p, like this here on screen. From this point, I don't necessarily want to go into how to take the derivative of this function just quite yet, as it requires the chain rule, and I'm going to save that for another video. This example was more or less meant to get you thinking about the Pythagorean trigonometric identities. All right, on to the next example. On this slide, we are being asked to find the second derivative of f of theta. So here's the first derivative. What is the second derivative of f of theta? And I think this time we're not gonna be able to avoid the product rule. So f prime of theta is 3. minus, so I'm going to have two functions here. There's one, here's another. And the way I do this is I use the product rule, and I'm going to take the derivative of the first, which would be 2 in purple, there we go, 2 theta. The derivative of the first times the second plus the derivative of the second times the first. And since this product is coming after a subtraction, we will need to make sure that this is all within brackets, because when we take the derivative, we are subtracting the derivative of this entire term. And the derivative of this entire term is right here. So we have to keep that subtraction there. So I suppose the next step here would be to distribute this negative to this term and this term. So we can rewrite that f prime of theta equals 3 minus 2 theta cosine theta plus sine theta theta squared. And in fact, I'm going to write that a little bit more nicely with the variable out front. So theta squared sine theta. There we go. In parentheses around these. There it is. From here, we will take the derivative again. Now, thankfully, the derivative of a constant is 0, so this is 0. But we will have to use the product rule now twice. So there's 2 theta, that's one function of theta times another function of theta, and this time, in this case, cosine theta. And then it's here again, theta squared times sine theta. So the second derivative, f double prime of theta, will be, let's see, negative 2 times the derivative of the first, so 1, times the second, so cosine theta, plus the derivative of the second, negative sine theta, times the first theta. All right, so that was the first one. And then you have to run through a product rule of the second term as well, and you'll get this. Derivative of the first times the second plus the derivative of the second times the first. And then all you have to do from here is simplify. Boy, simplification is a lot of fun, huh? So we have to distribute a negative 2 here and here and make sure we're writing things in the correct order. For the first term, we'll get f double prime of theta equals negative 2 cosine theta plus 2 theta sine theta. In the second term that we did over here, we're just adding this here. There were no negatives to contend with, so we can just copy that down. So plus 2 theta sine theta, what else do we have? Plus theta squared cosine theta. All right. From here, you can notice that we have theta sine theta and theta sine theta here. In fact, we have 2 of those and 2 more of those, so that should give us 4 theta sine thetas. And then everything else we cannot combine in any way. In this term, we have some cosines. In this term, we have some cosines. Oh, I guess we could factor a cosine out of these terms. Let's do that. So we can say plus cosine of theta times, that would be theta squared minus 2. And I think that's as simplified as we're going to get here for the derivative, or the second derivative of this original function. For the final example of the video, we are going to find the derivative of this function a, which is equal to this nonsense. We're going to find the derivative of that with respect to theta. So in order to start this, we can start out with dA d theta. The derivative of a with respect to theta is equal to the denominator, sine of theta, times the derivative of the numerator. So this will be cosine theta plus sine theta. And then we will subtract the numerator, sine theta minus cosine theta, times the derivative of the denominator, which is cosine theta, all over the denominator squared. So sine squared theta. Ooh, that's a lot. All right, so now all we have to do is simplify the top. Shouldn't be that bad, right? All right, so when we distribute sine here and here, we will get sine of theta cosine of theta plus sine squared of theta. And when we distribute the negative here and here, as well as the cosine from behind here and here, we will get the following. Let's see, we will get minus sine theta cosine theta plus cosine squared theta, all over sine squared theta. Okay. Now we look for like terms. So I see a term that has sine and cosine. I have another term that has sine and cosine. We have one of these, and we're taking away one of these, so they actually just reduce away. That's pretty nice. So long, so long. And so in the numerator, it looks like we're just left with sine squared plus cosine squared. Are your Pythagorean trigonometric identity senses tingling? Because they should be. So we have sine squared theta plus cosine squared theta all over sine squared theta. And the numerator is just equal to 1. So here is the derivative of that function. This calls back to the, as I mentioned, the Pythagorean trigonometric identities. So make sure you know those to make your derivative life easier. Thanks for watching.